Hi. Now we are going to see theory alternating current. Last class we have seen about electromagnetic induction, that is EMI. So now we are going to see alternating current. What is the basic difference between AC and DC, alternating current and direct current? For all domestic supply in India, we are using alternating current with a frequency of 50 Hertz and voltage supply of 220 volts. Alternating current means bidirectional current. Direction is not constant, direction is varying, bidirectional. This is AC. Major difference. DC means it is unidirectional current. Unidirectional current is DC, bidirectional current is AC. Then frequency of AC. Some countries we have 50 Hertz, some countries we have 60 Hertz frequency. So there is a frequency for AC. DC there is no frequency. Frequency is 0. Time varying we call it as frequency. Since the current is direct, there is no question of time variation here. There is no time variation means frequency is 0 only. Okay. So this is direct current. So in this chapter, we are going to talk what is called RMS value of AC, IRMS. Alternating and RMS value of alternating current. No sir, I want alternating voltage. No problem. RMS value of alternating voltage. There should be a common factor for AC and DC. You take a resistor, allow some alternating current to pass through for a given interval of time. What is the heat energy produced? You calculate. Say 2 minutes, 100 joules of energy is produced. Same 2 minutes, same 100 joules, how much amount of DC is used to heat the resistor or to heat the coil, whatever it is. Amount of heat energy and time taken is same. Then this much amount of DC and this much amount of AC is equal. That place only we can compare these two. High voltages, it is very, very difficult to control AC. DC easily can be controlled. Okay, so we are not going in detail how DC is advantageous or how AC is advantageous, that and all. Okay. IRMS is equal to maximum current by root 2, IM by root 2. ERMS is equal to maximum voltage by root 2. IM by root 2. 1 by root 2 is 1 by 1.414. That is 0.707 IM. 0.707 EM. VM we can write, the EM we can write, small EM we can put. No problem. Maximum voltage, maximum current we are representing. That's all. Okay. Now, previous topic in electromagnetic induction, because this is part 2 we are seeing. Already we have seen part 1 long back. So this is part 2. Previous topic in electromagnetic induction part 2 we have seen. Whenever there is a change in magnetic field or magnetic flux linked with the coil, and EMF is induced. So there is a current in the circuit. That's all we have seen. What is the phase relation between the current and voltage produced there? That we have not seen. So when you consider a pure resistive circuit or pure inductor circuit or pure capacitive circuit, what is the phase relation between current and voltage? That's what you're going to see here in detail. Then all the three put together, that is RLC, resistance, inductance and capacitance put together. What is the phase relation? One by one we will see. Circuit containing only resistance. Only R. Resistor connected with AC generator. This is AC generator. AC generator principle, you know, conversion of mechanical energy into electrical energy, producing an EMF of Vm sin omega t or Em sin omega t, where Vm is the maximum value of voltage. Okay, fine. Current by Ohm's law, V is equal to IR. So I is equal to V by R. V is nothing but Vm sin omega t by R. Maximum value of voltage by resistance. Maximum value of voltage by resistance, we call it as maximum current. That is Im sin omega t. So equation 1, Vm sin omega t. Equation 2, Im sin omega t. So both current and voltage are in phase with each other. There is no phase difference. So when you draw a graph, ERI, this is theta or omega t. This is the graph for voltage, means same for current also. This is I. 0, pi, 2, pi. Both starts with 0, positive maximum, 0, negative maximum, 0. That means the phase difference between current and voltage is 0 here in the case of circuit containing pure resistance. Okay. So this is first topic. Next, circuit containing only L, that is an inductor. Circuit containing only L. This is a coil connected with AC generator of voltage value Vm sin omega t. Here also we are going to see what is the phase relation between current and voltage. By Kirchhoff's second law, that is loop rule. This is voltage generated from the AC generator. You know very well, for an inductor, the EMF psi is equal to minus L into di by dt. In self-induction theory, we have studied, psi is the induced EMF that is equal to minus L into di by dt. So this is the EMF for the inductor. This is the voltage for the AC generator. So by loop rule, V minus of minus psi is equal to 0. Algebraic sum of the products of current and resistance taken around a closed network in a circuit is 0. Okay, so V is equal to V plus I is 0. V is equal to minus I. What is V here? Vm sin omega t is equal to minus of minus. So that will become L into di by dt plus. Already this minus sign we have included here. So minus I only we are done. L into di by dt is minus I. Okay. Di is equal to, this is equation 1. V is equal to Vm sin omega t is equation 1. From this you calculate current. Di is equal to Vm by L sin omega t dt. We have to integrate the equation. Integral di is equal to minus integral Vm by L sin omega t dt. Integral di is I. Vm by L is constant. Take it out. Sin omega t integration. Integration is minus cos omega t by omega. Differentiation is sin theta is cos theta. Integration is sin theta is minus cos theta. So here minus cos omega t by omega. So minus Vm by L omega. We can write cos omega t as sin 90 minus omega t. Sin 90 minus omega t is cos omega t, or sin 90 plus omega t is also cos omega t. Okay, fine. Now, take this minus sign outside. What will you get? I is equal to minus Vm by L omega sin minus of omega t minus 90. Sin of minus theta. Sin of minus theta is minus sin theta. So I can write I is equal to sin of minus theta, minus minus plus Vm by L omega sin omega t minus 90. Current is equal to voltage by something. So that something is called resistance. Already we are using the term resistance R. So some other new term we are going to use here, that is called reactance. Reactance is also in the family of resistance only. Since this is inductor, we are using inductive reactance. Inductive reactance we are going to see. That is Vm by XL sin omega t minus 90. Maximum voltage by resistance, we call it as maximum current, Im sin omega t minus 90. Now you compare equation 1 and 2. Equation 1 is sin omega t. Equation 2 is sin omega t minus 90. That means what? Voltage leads the current by 90 degree. Or current lags behind the voltage by 90 degree. Okay. So here XL is equal to L omega is called inductive reactance. resistance offered by the inductor. That is the meaning. And Vm by XL is equal to Im, maximum current. So, when you draw the graph between voltage and current, this is voltage E. Current is lagging behind the voltage. So you have to start with a negative value. Here you have to start. This is I. Maximum value Im. Here maximum value Em or Vm. Vm maximum. Voltage is leading the current by a phase value of 90 degree, pi by 2. This is 0, pi to pi, whereas this lagging we call it as 90 degree lagging. Frequency of DC is 0. Implies XL is equal to L omega L into 2 pi F. That is 0. So, in the case of DC, the resistance offered for an inductor is 0 because frequency of the DC is 0. So, hence XL, inductive reactance for a DC is 0. Okay. So, this is the second part. So, first part in resistance we have seen current and voltage are in phase with each other. Second part we have seen voltage leads the current by 90 degree or current lags behind the voltage by 90 degree. Now, third one you are going to see circuit containing only capacitance. Circuit containing only capacitance C. So, capacitance circuit with a generator value Vm sin omega t. For a capacitor, V or psi EMF is Q by Q is equal to CV or B is equal to Q by C. Charging and discharging of a capacitor. First chapter electrostatics we have studied. So according to that, the relation connecting potential difference and capacitance is or EMF across the capacitor is psi is equal to Q by C, where Q is the charge. So, by loop rule, Kirchhoff's loop rule, V minus psi is equal to 0. V is equal to psi. Vm sin omega t is equal to Q by C. But we need a relation connecting current and voltage only. Here we are having a charge. So there should be a relation connecting current and charge. What is the relation? I is equal to dq by dt. I is equal to d by dt of Q is C into V. That is d by dt of C Vm sin omega t. C Vm you take it out. constant. Sin omega t differentiation. Cos omega t into omega. I can rewrite this equation C omega into Vm into sin 90 plus omega t. Okay. I is equal to, you can take this C omega to denominator without changing its original value. Original value should not be changed. How to take it? Vm. Denominator we can write this as 1 by C omega sin 90 plus omega t. Why we have to write like this means current is equal to voltage by resistance. So by something should be there. That something should be the resistance offered by the capacitor. As we have mentioned in inductor, this is called capacitive reactance. There XL inductive reactance we have seen. Here XC capacitive reactance. So I is equal to Vm XC sin 90 plus omega t. Maximum voltage by resistance we call it as maximum current Im sin 90 plus omega t. Equation 2. Equation 1 is Vm sin omega t. Equation 2 is sin 90 plus omega t. What is the meaning? Current leads the voltage by 90 degree in pure capacitive circuit. Inductive circuit, current is lagging behind the voltage by 90 degree. In capacitive circuit, voltage is lagging behind the current by 90 degree. Okay. So here, Xc is equal to 1 by C omega is called capacitive reactance or resistance offered by the capacitor. And Vm by Xc is equal to Im, maximum current. So when you draw the graph for current and voltage, E or I, theta or omega t, this is the voltage. Current is leading the voltage. I. Or if you take this as I means, voltage will come on the negative side, like inductor what we have represented. Okay. For a DC, frequency F is equal to 0. Therefore, Xc is equal to 1 by C omega, 1 by C into 2 pi F, 1 by 0, that is infinity. That means for a DC, capacitor will give infinite resistance. That means what? Capacitor blocks DC. It allows only AC to pass through. Major concept here. Very, very important note. Capacitor blocks DC because the resistance offered for the DC in capacitor is infinity. So no current flows. For AC, X is equal to 1 by C omega. For DC, Xc is infinity. That means it blocks DC. Now, all the three put together, we are going to see what? Inductor, capacitor, and resistor. LCR circuit or RLC circuit. So, before going to pure inductor, before going to RLC, for resistance, current and voltage, same direction. For inductor, voltage is leading. For capacitor, voltage is lagging behind the current. So keep that three things in mind. RLC in series. Very important question this is. Resistance, inductance, capacitance connected to a AC generator, RLC. V is Vm sin omega t. We cannot write just like Ohm's law or capacitance, resistance, potential across a capacitor, or for a self-induction, what is the EMF line. Here all the three put together. So we are going to draw a vector or phasor diagram to calculate the resultant voltage or resultant resistance. In terms of resistance and voltage, current also can be calculated. Okay. So that vector or phasor diagram, we have 2-3 forms. Simple form. You can see one similarity in here. Only resistance, only inductance, only capacitance. In all the three, direction of current is same. That is along positive x-axis. So in RLC also we will take into account current will be along the positive x direction. Okay. Now, this is what current. For pure resistance circuit, VR. Voltage and current are in phase with each other. For inductance circuit, VL. Voltage leads the current by 90 degrees. For capacitance, VC. Voltage lags behind the current. First, we will calculate the resultant of VL and VC. Because we have three different directions, VR, VL and VC. Three different directions, we cannot calculate the resultant. So make it into two. Then find the resultant. You know very well, potential across resistor is VR, across inductor is VL, across capacitance is VC. So, potential difference across R is VR, I into R. Potential difference across L, that is VL, I into XL. Potential difference across C, VC, I into XC. Okay. I. For all the three, I is constant. Okay. When you compare VL and VC, IXL, IXC, I is constant. So we have to see whether XL is greater or XC is greater. Because out of these two, first we will find the resultant, then we will use it for VR. So we will assume here, let XL greater than XC. XL greater than XC. When you say XL greater than XC, VL should be greater than VC. So you will get the resultant here. What is the value? VL minus VC. So now VL minus VC is one direction and VR is another direction. You can find out the resultant. This is the resultant voltage V. O, A, B, C. Between the resultant voltage and the current, the phase angle, let it be phi. First, the resultant voltage V we will calculate, then resultant resistance will calculate. Then to calculate the angle between these two, tan phi we have to calculate. One by one we'll see. From triangle BOA, OB square is equal to OA square plus AB square. OB square is V square. OA square is nothing but VR square. AB and OC are equal and parallel. So we can write VL minus VC the whole square. So V will be root of VR square plus VL minus VC the whole square. This is the resultant voltage. Now, sir, in terms of current, I want to express. You substitute these values here. What do you get? V is equal to VR square is IR the whole square. So, I square R square. VL, IXL, VC, IXC. So, I constant, XL minus XC the whole square. This is also square. So, I square. Take it out. I square common. When you take out of the root, it will become I. R square plus XL minus XC the whole square. So this is a resultant voltage for the circuit containing resistance, inductance and capacitance, RLC. Now, resultant resistance. No, sir, first current I want, sir. Current means V by total resistance. This total resistance we call it as V by I, we call it as current. I mean, V by I, we call it as resistance. That is root of R square plus XL minus XC the whole square. Already resistance we have. So that terminology we cannot use. Reactance, inductive reactance we have used, capacitive reactance we have used. For all the three put together, we have to use some other term that is called impedance. Resistance, reactance, impedance, all are resistance family only. Depending upon the need, we are taking that all. So, Z, which is called impedance. Sometimes they will ask to calculate what is the resultant voltage and resistance for LR circuit. LR circuit means inductance and resistance only, no capacitance. Simply you ignore this XC value. R root I, V is equal to I into root of R square plus XL square over. Here, Z is equal to root of R square plus XL square. Ignore XC, no capacitance. No, sir, LC circuit I have. Remove this. XL minus XC the whole square. RC circuit you have. R square plus XC square. How plus XC square means? Here minus sign whole square. So minus when you square it will become plus. Here you may have one more doubt. What doubt means? Sir, we have assumed XL greater than XC. Suppose XC greater than XL means what will happen? When you say XC greater than XL, you will get the resultant here. In that case, VC minus VL will be there. Whether it is VL minus VC or VC minus VL, resultant voltage, current and impedance values will not change. Simple man. Here you can put XC minus XL. So same value. Whole square. Negative sign will not come. Whole square. Here root of R square plus XC minus XL. Same concept. Value will not change. So induct current leads the voltage. If you say XC greater than XL, current leads the voltage. This is V is equal to Vm sin omega t. I is equal to Im sin omega t minus 90. Why we are putting like this, sir? Not minus 90 here, minus 5. When you put minus 90, it will become only capacitance, only inductance. Current lags by 90 degree. Here RLC, what phase angle? 5. Im sin omega t minus 5. Minus because current is lagging according to our example. If you say XL less than XC, it will become sin omega t plus 5. Current leads by 5. What is the resultant phase angle? Tan phi we have to calculate. So from triangle BOA, tan phi is equal to opposite AB by adjacent OA. What is AB? AB and OC are equal and parallel. So we have VL minus VC. OA is nothing but VR. So tan phi is equal to VL minus VC by VR. What is VL? IXL minus IXC by IR. So I cancels everywhere. XL minus XC by R. Resultant phase angle. Okay, this is most important question. RLC circuit, whether it is a state board or CBSE. For both the boards, this question is very important. Okay, now we are going to see resonance in RLC. Resonance. What is called resonance? Generally, in mechanics, we have studied sonometer example we have seen last year. When the tuning fork is struck and kept on the wooden board of the sonometer, the frequency of the tuning fork and frequency of the wire which is vibrating, when these two matches, there exists a resonance condition. When you do it in practical, the wire will vibrate with maximum amplitude. Then the paper rider, what you have kept inside, is thrown off. So frequency of the wire and frequency of the tuning fork, these two matches means the resonance condition. Like that. One particular case you have studied, you have seen XL greater than XC. Another case you have seen XC greater than XL. So there should be a case between these two common. That is when XL is equal to XC. XL is equal to XC means L omega R represents resonance. 1 by C omega. So omega square is equal to 1 by LC. Omega is 1 by root of LC. Resonant angular frequency. This is called resonance angular frequency. Resonant frequency I want, sir. You can write. Omega is 2 pi f. That is 1 by root of LC. F is equal to 1 by 2 pi root of LC. Resonant frequency in the case of RLC series circuit. There is one concept known as Q factor or Q value, where current is maximum. At resonance, current is maximum. Formula Q is equal to voltage across L of C by applied voltage. This is the ratio. At resonance only, it gives a peak. Quiescent point, Q point. That is across L or C. We will write this as across L, IXL. This is IR. I cancels. That is L omega by R. At resonance means omega R it is. So L by R. What is omega R? 1 by root of LC. L you can write as root L into root L. One root L get cancels. So we can write 1 by R into root of L by C. This is Q factor or quality factor, where current is maximum. What is the current maximum? You are drawing the graph between frequency versus current. Frequency versus current. This is F for resonant frequency. So at resonance, you can see here, there is a maximum current. So up to the resonant frequency, as frequency increases, current increases. Beyond the resonant frequency, as frequency increases, current decreases. So here you can say R is minimum. So current is maximum. Here R is maximum. So current is minimum. Okay. Next, power in AC circuit. Power is a product of voltage and current. Vm sin omega t, Im sin omega t minus phi. You can very well put minus phi or plus phi, no problem. Calculate average power generated over one complete cycle. Average power generated over one complete cycle. So, when you simplify by integrating 0 to 2 pi, average value of current for one full cycle of AC, the answer is Vm by root 2, Im by root 2 into cos phi. Vm by root 2 or Vm Im by 2 cos phi or Vm by root 2 is Vrms. Im by root 2 is Irms. Cos phi we call it as power factor. Vrms into Irms is apparent power, actual power or average power by apparent power. This is called power factor. We have drawn one graph here. Previously in RLC, we have drawn a graph. This is VR. This is VL. VL minus VC. This is a graph. When you calculate cos phi here, adjacent side by hypotenuse. Adjacent side is VR. Hypotenuse is V. So cos phi adjacent side is IR by I into root of R square plus XL minus XC the whole square. R square plus XL minus XC the whole square is what? I cancels. R by Z, that is called impedance. R by Z. Next question they will ask, what is the power factor for resonant circuit case? Resonant circuit, Z is equal to R. You apply XL is equal to XC here. Put XL is equal to XC. What is happening? XL is equal to XC means this term will become 0. Root of R square is R. R cancels. Cos phi is 1. Cos phi is 1 means phi is equal to 0. So the phase angle between current and voltage is 0 where in pure resistive circuit. Even though we are using RLC circuit, the phase angle is 0 for a simple reason. Resistance XL and resistance XC both are equal. So at resonance case, power factor R by R, that is 1. Okay, fine. Next, electromagnetic induction chapter. Finally, we have seen transformer. There, long range power transmission we have to discuss. In long range power transmission, if you are using a transformer, the power loss is minimized. If you are not using a transformer, there is a maximum power loss. That's what we are going to explain. So, assume it is almost equivalent to a problem. Let V is 220 volts. Power input is 110 kilowatts. Resistance 0.33 ohms. Through the cable only the current is passing through. That cable resistance is 0.33 ohm. Then what is the power loss? Power loss is I square R. That is nothing but V. I is nothing but P by V. The whole square into R. What is P? 110 kilowatts by V is 220 whole square into 0.33. So 2 times 1000 by 2 is 500, 500 square. 500 square is 25 into 10 power 4 into 0.33. 25 into 33 into 10 power 2. 25 to 25, 625, 25 into 8. So 825 into 10 power 2 or 82.5 kilowatts. See, 110 kilowatts only transmitted. In that 82.5 kilowatts lost. That means 75% of power is lost. There is no transformer used. If you are using a transformer, this is without transformer. With the transformer, when you calculate, what will happen? Let V in dash will be 100 times it is multiplied by a step-up transformer, let us assume. Using a step-up transformer, 100 times it is multiplied. So, power loss, PL dash I square R, that is 110 power by voltage, 110 kilowatts by voltage is 22 into 10 power 3 the whole square into R, 0.33. This is 5 times, 5 square 25, 25 into 0.33. 8.25 watts, 0.00825 kilowatts. So, 110 kilowatts transmitted, but receiving, power loss is 0.008, very minimal. But in the receiving end, we should give utmost care because 220 into 100 volt is transmitted. So the receiving end, we have to use a step down transformer to reduce this value. For domestic supply 220 volts. For cinema theater 440 volts. For industry 1100 volts. Depending upon the requirement, we can use a step down transformer at various levels. Okay. So this is a brief idea about long range power transmission. Then overall we have discussed about alternating current for a circuit containing only resistance, only inductance, only capacitance, and all the three put together. And finally we have discussed about power in AC circuit and the power factor in that. Okay. Thank you. We'll continue.